Okay, perfect. Let's now understand the identity verification circuits. Before going into the details of each of those circuits, let's first understand the architecture. So for that, let's go to Scotty-Drone and let's see how the data flows. So we have the identity verification circuits. This is the onboard function that has 3 gates, 2 authorizations. The first gate, it's a quiz commitment. So we're gonna make sure that this commit equals to a quiz hash. If that happens, the accreditation knowledge check passes. Then we have gate 2, the identity assert identity. We wanna check the signature, it's valid, it's trusted IDP, the identity provider, and the nationality, it's okay. And then for gate 3, we're gonna check the wealth assert coin value function. We're gonna make sure that the color equals to the TBTC color, the value is greater than 100, and then we're gonna do a temp deposit plus return. We are not gonna hold any value of the user. If all these 3 gates passes, then we're gonna make authorization insert on public key. We're gonna actually insert the user into the Merkle tree. So now let's go to the details and see how each one of these gates were implemented using Compact. So we are here on the onboard circuit. So we have this onboard function circuit where we are passing the quiz of type quiz result, input coin of type coin info, and the identity, which is a signed credential of type passport data. And in here we can see that we have 4 steps. The first step is a quiz answer match commitment. So we are making sure that the quiz, and we are doing a hash, it's equal of the quiz hash that we have already sealed in our contract. If it fails with a message, quiz has some incorrect answers. Then for step 2, the identity credential is valid. We're gonna check if that condition complies. So we're gonna do assert identity. We're gonna go through that circuit in a minute. Then for step 3, we have wealth greater than 100 TBTC. And again, we're gonna make assert coin value of this input. We're gonna go through that circuit in a bit as well. And lastly, if those first steps passes, which are the 3 gates, then we're gonna add to authorize investors. By authorizations, this is one of our public ledger variables, we're gonna insert into the Merkle tree the own public key, which is the user interacting with this contract, circuit in this case. So 4 checks in 1 ZK proof. Accreditation quiz answers committed via persistent commit, compared against a stored hash. The identity verification, it's a JubJub signature check, issuer trust, nationality filter. For the wealth check, we must hold more than 100 TBTC. It's a temporary deposit and return. And the authorization, it inserts investors' public key into the Merkle tree. Okay, let's go into detail how this identity assertion works and how it was declared using Compact. So for that, we have a circuit called assert identity, where we are passing our identity of type signed credential of type passport data. So first, we get a const called challenge of type field by running this command. Pretty much we are computing the challenge by using our identity signature, identity pub key, and identity credential. And then we are verifying by asserting that this passport data with the identity and the challenge calculated, it verifies correctly. Otherwise, the supplied identity is not signed by the supplied public key. This is gonna fail. Okay, then we compare that the identity pub key it's equal to the identity provider public key that we have declared during the creation of the contract. If it fails with a message, the supplied identity is not issued by a trusted identity provider. Okay, and lastly, we're gonna assert certain conditions. We're gonna make sure that the identity, credential, nationality it's equal to the allowed country 1 that we set up during the creation of the contract, or the identity, credential, nationality is equal to the other allowed country, which is code 2. If those fails, we're gonna have a message saying the holder of the identity is not from an allowed country. So the privacy boundary, the entire passport extract, name, date of birth, passport number, sex, expiry, stays in the witness. The circuit proves 3 things. The credential is signed by a trusted issuer. Second, the nationality matches. And third, the signature is valid. Only nationality is disclosed via disclose. Everything else, it's private. Even though the nationality is disclosed, this condition is not going to be updated on the public. It's just on the circuit. Okay, now let's take a look at the other function regarding the coin value assertion. So in this case, we have a circuit called assert coin value, and we are passing our input coin of type coin info. And we are declaring the constant coin by grabbing the input coin, which is the prop of the circuit. Then we are doing some assertions. First, the coin color should be equal to the TBTC coin color declared in our contract. Otherwise, it's gonna fail with the message the coin supplied for verification is not TBTC. Then we're gonna assert that the coin value is greater than 100. If it fails, it's gonna give a message saying the coin supplied for verification has a value less than 100 TBTC. Then we're gonna receive the coin that it's part of how Midnight works. We have to receive that coin. This is a function available within the standard library. And then we're gonna send immediate the coin to left, which means that it's of type C swap coin public key, and the own public key it's the user interacting with this contract, and coin value. So this means that we are sending this coin, this amount of value to this person on public key, the amount of money that we receive. So this circuit, it's not holding any amount of value. It's just receiving money, checking conditions of that money, and then returning that money back to the user. So this is temporary deposit pattern. The contract receives the coin to verify it's real and meets the threshold, then sends it right back. The investor doesn't lose their TBTC. The contract just needs to prove they have it. Okay, let's take a look now at another circuit, which is the buy and sell after authorization. So we have here the name of the circuit, which is Midnight Real World Asset.compact, and the name is buy THF. We accept as a prop an input coin of type coin info. Let's see how this circuit is implemented. First, we're gonna make sure if the Merkle tree membership passes. So it's authorized send, and we are making sure that the on public key, the one interacting with this circuit, this contract, it's authorized. It's in the Merkle tree. If it passes, then we are okay doing the rest of the circuit. If that on public key is not part of the Merkle tree, then this circuit is gonna fail. Okay, so if the user is inserted already in the Merkle tree, he's authorized. Then we're gonna get the coin by disclosing the input coin passed to the circuit, and we're gonna do some assertion. First, we're gonna compare that the color it's equal to the TBTC coin color. Then we're gonna make sure that the value is greater than 0, and then we're gonna receive that coin, and we're gonna write the TBTC coin into the contract. So one receives TBTC from investor, and the other write TBTC, it adds to the contract TBTC pool. Then we're gonna send the result. So we are calling this circuit called send. This is part of the standard library functions, and we are sending the THF to the on public key with the amount of coin value. So this sends THF to investors, one-on-one rate in this case. This is this specific contract logic. It can be changed in other logics. So then we're gonna handle the change. So we have this change, send result, and we're gonna receive the change. So the way coins works in Compact with ZSwap in this case, it has the same structure of UTXO. So we send all the coins and then we have to handle the change. So after we receive the change, we have to receive it again in our contract. So we call this receive circuit, which is part of the standard library of Compact, and then we write coined THF. So this pretty much handles the change and put it back into the contract. So in this case, we are receiving a change, but normally we were using left on public key, which is a ZSwap coin public key. But now, since we want to update the contract pool with this change, we're gonna choose right, which is not anymore ZSwap coin public key, but it's a contract address. And we are receiving the change and updating our kernel self. This kernel self, it's a function from the standard library that corresponds to the contract itself. So we're saying, I want to update this contract that I'm interacting right now. So the authorization gate, every trade starts with its authorized send, a Merkle tree membership proof. If you haven't gone through the onboarding, the proof fails before you can touch any tokens. So before this slide, we were talking about this authorization and passing the 3 gates. So here it's a explanation of how this JubJub signature verification works. So this is, you don't have to learn that from scratch. It's already integrated within modules, so you can use it in your contract just by grabbing these modules. Soon this is going to be integrated into the standard libraries as well. So we have the sign with the Schnorr on JubJub, and then we have the verification process to verify the signature using this Schnorr on JubJub. We were taking a look at the implementation of the Schnorr. Let's go back here really quick, right? As I mentioned, you don't have to learn and implement this logic from scratch all the time. This has already been implemented and you can reuse it. But let's take a look of how this is implemented in Compact. So we have here the Schnorr sign circuit. It's a circuit called sign. We can see that we are passing a credential of type T, passing T as a general type, and passing some ZK of type field. We can see here that we are using some circuits available within Compact to interact with a elliptic curve. In this case, elliptic curve mul generator, and then we have some transient hash. You can see that again we are interacting using the elliptic curve, doing the compute challenge, and then signed the credential. Down here we have the circuit for the verification of the Schnorr circuit. So we are passing the credential, which has already been signed, and passing the challenge. All those were calculated during this signed circuit. And then we are verifying the challenge. We are verifying the elliptic curve mul. And if all this passes, it means that that message, this credential, was signed by an approved signature. Okay, this important part here I want to mention as well, which is the passport data extract. So we were mentioning that we are transforming a passport metadata into a new metadata that is more friendly for ZK construction. So in this case, now the contract looks like this. You can see that different fields, for example, document code, issuing organization, holder name, etc., all those are of type field, and depending on the function of each field, it's going to have more bytes than the others. So for example, this document code, it has 2 bytes. The issuing organization has 3 bytes. In the case of a holder name, it's going to have 39 bytes, and so on. And so in this way, we're going to be able to interact with ZK much more friendly. We can see here that the same machine readable zone on every passport worldwide. All 14 fields are encoded as field types. Little endian begins for ZK arithmetic. Of all these fields, only nationality ever gets disclosed. Okay, perfect. So this is something really nice. You can see how we can interact and transform data with the purpose of making everything more friendly for the ZK construction.